All right, friends and neighbors, welcome back. We are doing CCNA Volume 2, Chapter 11, Quality of Service. Now, there's a lot of big ideas in this chapter, so I thought we would do it in two parts. So we'll do lots of capture analysis as we go through this, but yeah, there's a lot of stuff in this one. So as always, we'll do the key topics. The exam section for this one is IP services explain the forwarding per hop behaviors for quality of service. And there they all are, right? Classification, marking, queuing, congestion, policing, or policying, depending on how you pronounce it, shaping. And the context that I like to wrap this in is router policies, where we examine traffic at the ingress, we make some decisions on what we see, and then we apply some quas policy or quas technique. So you can see that if you were trying to wrap your head around all this and trying to understand all the packet fields that we're talking about, it's a lot. So I'm going to break it up into two parts. And then the do I know this already questions, and we'll split those up into two parts as well. And there they all are. There's the key topics. That's for the whole chapter. The things that we're going to talk about in this particular video are the first group there. So the four quas characteristics, voice and video quas requirements. These will be the settings that are the targets that we have. IP precedence and IP DSCP marking fields, 802.1q class of service, and then the trust boundary with IP phones, and really that's where you start figuring out when you're going to accept the classification. And then we'll do queuing and all of the rest of the management stuff on in the next video. So at the beginning of the chapter, we start talking about all and these are the four quas characteristics. So if you take a look at the graphic above me here, and we consider that one side is the LAN of this router and one side is the WAN. And it is very typical to see LAN bandwidth exceed WAN bandwidth. So that is to say you got a gig network on the inside and maybe you're paying for, fiber connection on the outside that's 500 meg, or maybe, some other slower connection, maybe even. And so now imagine that you've got all of this traffic heading for the web. And so lots more traffic coming from the LAN side, and the WAN side can only forward traffic at a certain rate. And of course, on both sides, we've got the queues. Now, technically, we've got input queues and output queues, or ingress and egress, but at this point, we're just talking about traffic flowing in one direction. And the question is, what does that router do with all of this traffic, right? The traffic is coming in from the LAN side, and the queue is starting to fill up, right? You're beginning to run out of memory, maybe. What does the router do? Well, you can handle this in a number of different ways. You can do bandwidth controls, you can do queuing controls or queuing algorithm changes, you can drop packets. There's all kinds of things that the router might do. And the question is, what's the right thing to do given the kind of traffic that you have? Now, our first measurement or our first characteristic is bandwidth. Usually the speed of the link. So on Ethernet, we think, right, 10 megabit, 100 megabit, gigabit, and then maybe even 10 gigabit. And that's how we usually think about things, and that's link speed. But we also might think of that in terms of the capacity of the link. And so how fast can you forward traffic? Now, it is never the case that we can forward constantly at link speed. So that is to say that if I've got a gig link, I don't send 1 gigabits of data, right? Because in between frames, we have to do this interframe gap. So that's one place where we have a little bit of overhead. Now, a lot of times we think, oh, well, bandwidth is how much data that I'm sending. And that's not true either. That is throughput. And so when we think about application data is wrapped up in headers, and then that has to be sent across the link. And so if you're thinking about application throughput, it's going to be less than the overall capacity or speed of the link. But bandwidth is one of the first things that we think about when we start thinking about characteristics. Now, delay or latency is another characteristic, and this can be measured in one way, or it can be out and then back. And so we have two ways to think about this, and it is the time between a packet is transmitted and the time that it either arrives at the destination, so that's one way, or the time that it takes me to get a message out and then get a response back. So that we sometimes think about that as two-way delay. So that's also sometimes referred to as response time, but it depends on if you're looking at message or you're trying to understand how fast an application can respond. Now, jitter is probably the most complicated one of the group. It is the difference between expected and actual arrival time. And the book describes this in terms of delta t. And so if you've got a series of packets and every packet is separated by 3 milliseconds in time. So I get one packet, 3 milliseconds later I get another packet, 3 milliseconds later I get another packet. There's no variation in arrival time. So the jitter is 0. But if some packets arrive within 3 milliseconds, but then the next packet waits 5 milliseconds, 10 milliseconds, 15 milliseconds, and I expected it at 3, then I've got jitter. And so in the example that I've got here is that if the normal wait time was 3 milliseconds and the next packet was received at 5 milliseconds instead, then my jitter is 2 milliseconds. And what jitter results in is unreliable application performance. Now, packet loss is pretty straightforward, right? I lose a packet. So what percentage of packets fail to reach the destinations? Pretty straightforward problem. For TCP, it's much worse than UDP because TCP tries to recover from these losses and UDP doesn't care. Some applications and some games like Call of Duty, right on the interface, it tells you what your packet loss is. Now, of these things, the number one cause of poor perceived application performance or voice call quality is delay. It is the number one problem. So if you have a whole bunch of applications, the basic idea of quality of service is that we prefer one application over another based on the requirements of that application. So for example, we might prefer voice over IP over FTP. Now there are lots and lots of types of traffic, and every kind of traffic has its own requirements. Now, generally, we break this up into a couple of categories. For example, real-time versus non-real-time. Now, real-time is traffic that we need to have a timely response, or it has to happen in a particular period of time. So, for example, if you're getting telemetry, if you're having a conversation with somebody, you can't have delay or variation in performance for those. You need those to be real-time. Non-real time is, look, it'd be great if we get this done at some point, but we just don't want to wait too long. FTP is an example. A website is another example. A website, you click on the link, and you're okay if it loads, it takes a little bit of time to load. We just don't want it to take too long, and otherwise we'll navigate away from it. Now, other kinds of traffic can be constant bit rate, right, where you see the data flowing at a constant series of packets. And then there's bursty things where you make a request and all of a sudden there's a lot of traffic and then it peters off. Now, user applications such as the web or such as messaging or email, these kinds of things require a certain performance so that the users get a certain quality of experience. So that's another measurement. Now, that's totally a user measurement thing. How's that thing going? How's it working? It's working pretty good, so I have a good quality of experience. Now, these are things like you're working on financials and you're talking with a database and you make a query and the database takes forever, so you have a low quality of experience, or there's good response time. If you're doing Zoom at the end of a Zoom call, a lot of times it asks you about the quality of your connection, and there's just two answers. It was great or it wasn't so good, and that's a quality of experience measurement. Now, because of these kinds of things, business critical or core applications might be given priority handling. That is to say, we might say we're going to prioritize in some way, we're going to measure something, and we're going to say, look, this is a really important application, we're going to give it priority. For example, we might handle its packets before another application's packets. the non-iterative or non-user based or non-response based applications, their performance might not matter as much. Now, two really important examples that we have in the communication world today are voice and video. And again, these can be thought of as being one-way or two-way. One-way would be streaming or when you're listening to music. And two-way clearly are things like VoIP. And for these kinds of applications, performance is critical. So how you set up your network to ensure these arrive can be part of your quality of service strategy. Now, voice over IP and video that's two-way can be thought of as two flows. Now, a flow is packets moving from one source to one destination. But because voice is two-way, there's a flow of packets from me to you, and then there's a flow of packets from you to me. So these are two flows. And when we think about the bandwidth required for voice over IP, that comes down to something called the codec and then the encapsulation that we do. So when I'm communicating, something is converting my voice to digital or electrical signals. The thing that does the digital to analog and analog to digital conversion is called a codec. The most popular codec in the world today is Ch11. And Ch11 encodes voice at a rate of 64 kilobits per second, 64K. But it takes a little bit more bandwidth to send all that stuff. So say about 80,000 bits per second. So that's the example that they use in the book. So it's not a lot of bandwidth. I mean, out of a gig link or a 10 gig link, how much is 64K? It's not very much at all. Even if I had 100 megabit Ethernet or 10 megabit Ethernet, we're talking about 64K. It's not a lot of capacity. But a high quality of experience is required. That is to say, those packets can't be delayed. I need fast response time. They need to get across the network lickety-split. And so that's the difference between saying, well, it doesn't take very much in the way of resources, and I don't care, this has really got to get across the network. Quality of service characteristics for voice over IP include things like one-way delay of 150 milliseconds. That means if you add up all the delay between the source and the destination, it cannot exceed 150 milliseconds. And that would include things like the codec, the creation of the packet, whatever the switch does, whatever the router does, whatever you do at the other end to decode this, all of those things add latency. The other thing that we want to avoid is packet loss, so less than 1% loss, and a jitter less than 30 milliseconds. And actually, we want usually less than 5 milliseconds. Now, video is similar. It requires more bandwidth, well, because it's video. So at a minimum, we need 384K. And then the higher in resolution you go, the bigger the images, the bigger the frames, right? We need more capacity, so on up to 20 megabits per second. Delay can be a little bit more forgiving, so we can get away with 200 to 400 milliseconds, although we start to notice things are going wrong. Same thing with the loss, less than 1%, and then a jitter. Again, keeping that pretty low, but not quite as bad or not quite the restriction as VoIP. Now, one of the things that can help us with one-way transmissions anyway is buffering. So we buffer up a certain amount of the video or the audio, and then we begin playing it. And that way, if there's losses or there's jitter, we don't notice it as much, and we're playing the things out of the buffer or out of the memory while we're waiting to catch up. Okay, QoS step 1 is called classification and marking. Now, the first couple of ideas here can be applied to either packets or frames. So it doesn't really matter if we're talking about IP packets or layer 2 frames. A lot of these ideas can be applied to both. So they both have a way to be classified or marked. And the other idea here is that QoS tools like bandwidth control or queuing, they lie in the path of packets. So we're talking about a flow, and so it's important to realize that there's a directionality. So we apply quality of service concepts or tools in a particular direction, we also might apply them in the opposite direction. Now, classification is the process of matching fields in a message to make a choice on taking some quality of service action. So this is very similar to ACLs, right? So when we built ACLs previously, we might say something like, well, it's okay for this IP address to go to that IP address as long as it's doing ICMP. Well, that's three fields that we were just looking at. We were just examining the source and destination IP address and then the protocol ID. And those would be what we might call our match criteria. Now in ACLs, we would say, oh, based on those, I'm going to permit or deny. But in this case, what we're going to do is take a quality of service action. So in this case, what we're going to say is, oh, well, I see your source and your destination IP addresses, and then the protocol, I'm going to allocate more or less bandwidth, for example, to this particular flow of packets. Now, that approach is going to be part of an overall institute or organizational quality of service plan for your whole network. But the problem with that approach of matching all those fields is that it's expensive. If every router along the way had to examine all of those fields, well, that would be labor intensive. It would be increasing delay, and we don't want to do that. In fact, in ACLs, we don't do that at all layers of our network design either. The core layer of our network doesn't do any of that stuff, right? So that's left to other layers of our network design. Same thing is true with quality of service. So what we're going to do instead is at the edge of our network, I'm going to classify all of this traffic. I'm going to say, aha, I've identified you. And then I'm going to mark that traffic. I'm going to say, I'm going to provide a value, just one value in this particular packet, and that's the only thing we have to look at. So that is the marking part. Now we have a series of fields that we use to do this. At layer 2, we can take the layer 2 class of service bits, and or we can look at the IP header fields, and then we can map those to something called the DSCP bits, or the differentiated services code point bits. Now there are other fields that we can look at. We can take a look at the 802.11 traffic ID, that's part of that standard, or the MPLS experimental bits that are in the tagging that we do with MPLS. But what we're going to focus on here is the layer 2 cost values and what's going on in the IP header. Now, what have we been talking about? If you remember back to VLANs and trunks, we know that I can put a VLAN ID in there, right? And this will tell the switches how to forward this traffic. But what we may not have talked about is the fact that we can also provide a quality of service bits. Now, these are the layer 2 class of service bits in an 802.1q trunking header. Now, these can be one way to classify this particular kind of traffic. Now, there's lots of other things that we can look at, right? We can go to layer 3 and we can look at source and destination IP addresses. We can look at the protocol. And then what we can do is mark this traffic by setting the differentiated services code point bits. And when we do this, in this case, it's set to an 8 or a class selector 1. That'll be important to us later on. When we set this value, this is a marked packet, and now we no longer need to process these other fields. Now, network-based application recognition, or NBAR. So there are a couple of flavors of NBAR, and the whole goal here is to realize that some types of traffic aren't easily identified by the same fields that you would use for ACLs. They might be more complex. And so we need to be able to do something beyond just matching well-known ports and protocol IDs and source and destination IP addresses. And this packet here is an example of one of those things, right? So this is a voice over IP packet. And here are a couple of fields that we might use to identify. There's the source and destination port numbers. We might use those, but we might try to identify the codec. We might identify the synchronizing source identifier and try to set up our flow based on that, or our quality service based on that. So there are additional fields that aren't as easy to grab with an ACL. Now, the book example has a bunch of things that might benefit from the use of NBAR, and these are the video on demand by Amazon or a Cisco IP camera, right? Security feeds, all kinds of stuff that might be going across your network that's not really easy to identify with just a straight up ACL. In addition, for some of these things, some of these field values change. All right, so let's talk a little bit more about marking IP DSCP and Ethernet class of service. You have an overall QoS plan. You decide, well, this is how we're going to handle voice. This is how we're going to handle video. This is going to handle, or how we're going to handle our mission critical applications. And so we're going to apply these values across our network. And so there are a couple things that we might realize about how we would specify the marking that we're going to do. So there are some very, very common examples. So in that 802.1q header, we saw that we can specify a class of service. Now the packet had a 7. We might say, well, we don't need that high priority. We'll just use a 5. We might describe a QoS plan for voice over IP as having expedited forwarding, for example. So you just lay all this sort of things out. And then we realize that one of the cool things about an IP header, particularly internal IP headers, is that they survive the entire path without being overwritten. So if I mark a packet, even if a router doesn't understand that, it doesn't change it or it doesn't get rid of it. Now, historically, at layer 3, what we've had is the IP type of service bits. And that was the early RFC for IPv4, right? 791, if you look in there, it has the IP type of service bits. Well, with 3 bits, there's only 8 possible values. But today, if you look at Wireshark, you'll see that there are no type of service bits. Instead, we see this differentiated services field, or differentiated services code points. So this is the field that exists now, and there are 6 bits instead, and we get 64 possible values. Now it's a byte of information, so the other 2 are the explicit congestion notification bits. It turns out that IPv6 also has a traffic class byte that's used very, very similarly. So we don't want to forget that we have that 802.1q header and its class of service, also known as the PCP for 802.1q. And we can map them together. So you can tell devices, when you see this layer 2 QoS, we want to map that to a DSCP value. And so devices actually have a mapping function for that. So hopefully we're still okay here. So let's talk a little bit farther about this marking stuff. Now, all kinds of devices can mark traffic. Now, typically we think of this as maybe a switch and a router thing, but many end nodes can actually mark their traffic as well. Phones do it all the time, hoping the network is going to accept their values. An end user might be able to classify its traffic as well. But we don't always just want to accept what these nodes send into the network. And so on our Cisco devices, we can say, we are now going to trust these values. And at that point, we have a trust relationship with the classification to the marking. In your network topology, you say, here is our trust boundary. And at this point, any classification that we see is now going to be trusted. Where other parts of the network might not be trusted, they would just be using values and the network devices would ignore it. Now within differentiated services, the DSCP bits, there are a couple of suggested or sort of standard marking values. One of the top dogs is expedited forwarding. So it has its own RFC, 3246, and expedited forwarding has a DSCP value that goes along with it, and that is also 46. Now, how would you tell if something should be marked as expedited forwarding? Well, you would say, what are my applications? Which one of those have a low latency, low jitter, low packet loss requirement? A really good example would be voice over IP. So you might say, well, that's expedited forwarding. And so you would set that value in your in your network devices. And then you would make quality of service decisions based on that value because you've marked the packets. Another one that's a little more confusing is AF, or assured forwarding, and there are 12 possible values because there are 4 queues and 3 priority levels for each queue. Now, just to show you what that looks like, over here on the side of me, we can see that there are these queues and then the drop priority, the drop precedence values. And so the idea is that you assign the AF values to these, and when things hit the queue, they will have low, medium, or high drop precedence. Then finally, we have the class selector bits. Now, these are very similar to the original IP type of service or IP precedence bits. And there are 3 bits here as well. And these are the values CS0 to CS7. Now, if you look above me here, we can see a couple of things. These are maps that a router or switch might use to move a layer 2 value to a layer 3 DSCP value, or a layer 3 type of service value to a DSCP value. So at layer 2, we have the class of service with its 8 possibilities. And for example, if you have a class of service of 2, that would correspond or be remapped to a DSCP value of 16. Very similarly, these class of service bits look a lot like the IP type of service bits, but these are at layer 3 instead of layer 2. And we have a similar mapping here. And so your policies, the actions that you might take, would be based on these markings that would be in the IP header DSCP bits. And so some guidelines for your traffic. Standard traffic, right? Nothing special about it. Might be a class selector 0, and voice over IP might be have a DSCP value of expedited forwarding. All right, so our part 1, do you know this already? Which of the following attributes do QoS tools manage? Remember early on that we could look at those characteristics. So that was A, B, and E, bandwidth, delay, and loss, packet loss in this case. Question number 2, which of the following QoS marking fields could remain with a packet while being sent through 4 different routers over different LAN and WAN lengths? We know from what we were just talking about, the IP header doesn't change. So that would be BC, either the IP precedence or type of service bits and the differentiated services code point bits. Question number 3, which of the following are available methods for classifying packets in Diff Serv on Cisco routers? Choose 3 answers. That was A, B, and C, the IP DSCP bits, the 802.1p class of service. This is the priority bits that we saw in the 802.1q header, and we could also do it with an IP-based ACL. So our part 2 look ahead, we'll do a quick review of classification and marking, and then we'll tackle queuing, shaping, and policing. And then we'll talk about congestion avoidance. So you got to remember that TCP. So that's TCP windowing and avoidance of congestion, right? How can we avoid having congestion in the first place? So this has been quality of service part 1. We covered packet flows, latency, packet loss, and jitter. A little bit of bandwidth there too, right? And then the big topic here was classification and marking, particularly 802.1q class of service, type of service for IP and IP, and DSCP bits. Now, before I go on this one, I will put in the show notes. I mean, I've done the policy builds that show you all this, but as a last bit here, let me show you a packet example. So here's a capture that I did earlier, and it's just a standard IP header. And we can see right here is the differentiated services code point values. And here now we understand this to be a class selector of 6. Now most traffic internally that doesn't have a quality of service policy associated with it, these will just all be zeros, right? So all of this will be zeros. This also shows you where the DSCP bits are. So in this byte of information, it's a C0 down here in hexadecimal, but it's a C0 because this first value is what? 8 plus 4, or 12, which is C in hexadecimal, and then 0 here. Now in this case, we're not doing 802.1q, so we don't see any layer 2, and we don't know what happened to get this here, but this is a marked packet with a DSCP value, in this case, class selector 6. So that'll about do it for quality of service part 1. And again, I'll put those other videos in the show notes. So like and subscribe for part 2 of QoS, where we tackle queuing and shaping and other good things. Until then, no matter how you're classifying or marking your packets, may your packets always reach their destinations. And this is quality of service. It's tough. There's a lot, but you can do this.